They almost missed it at first. The signal was so faint that 3 different observatories thought it might be noise, perhaps just interference, or maybe nothing at all. But Dr. Rahat Gaonkar at the Very Large Telescope kept watching, kept measuring through those quiet August nights, and what emerged from the data made him reach for his phone at 4 a.m, not in panic, but with the kind of quiet wonder that settles over you when the universe whispers something unexpected. The nickel emission wasn't random, or at least it didn't seem to be. There was something beneath the chaos, something subtle, a rhythm, faint but persistent. The ancient traveller from another star drifting at 57 kilometers per second through the space between Mars and Jupiter wasn't just outgassing in the way comets sometimes do, it was doing something else, something that made the measurements pulse, very gently, every 8 hours and 22 minutes, almost exactly, like a heartbeat buried in static, like a clock that had been set billions of years ago and was still, somehow, keeping time. Perhaps it means nothing. Perhaps it's just the way frozen volatiles sublimate as the object rotates, creating patterns that only seem organised to pattern-seeking human minds. But the astronomers who've been watching this visitor since July, tracking its slow brightening as it approaches the inner solar system, they're seeing something that doesn't quite match what comets usually do. And they're still measuring, still watching, night after night, as the glow continues. Hello there, and welcome to Earth and Beyond, where curiosity gets cosy, and the mysteries of space take the scenic route to slumber. Tonight, we drift towards something that appeared in our telescopes just a few months ago, an object from between the stars, that began to glow when it shouldn't have, a visitor carrying chemistry from another sun, waking up in the darkness far from our own. Before we step into that quiet mystery, let me ask you something simple. Where are you listening from? Right now. Maybe you're in bed, lights turned low, the weight of the day finally settling as you search for something to carry your thoughts gently away. Maybe you've got the soft glow of a screen in the darkness, seeking that particular kind of company that astronomy documentaries offer, the reminder that beyond our daily concerns, vast and ancient things are drifting through the cosmic dark. Or maybe you're somewhere in between, in that liminal space where the mind begins to loosen its grip on waking concerns and opens itself to wonder. Wherever you are, imagine for a moment that you could see beyond the ceiling above you, beyond the atmosphere, beyond the moon's pale orbit, out to where Mars traces its patient circle around the sun, and just beyond that orbit, moving inward on a path that will never repeat, drifts something that has travelled farther than any human-made object, farther than Voyager, farther than any craft we've ever launched, an object that spent perhaps 9 billion years crossing the galaxy, passing through clouds of dust and gas, witnessing stars being born and dying, carrying within its frozen depth the chemical signatures of processes that happened around a sun we will never see. If you find this sort of gentle exploration soothing, if you appreciate these quiet journeys through cosmic mysteries that help the mind settle before sleep, I'd be grateful if you gave the video a like, or maybe subscribed. It helps this small corner of the internet reach others, who might also enjoy drifting through the universe this way, at a pace that doesn't demand urgency, only attention. Now then, let's move carefully into that mysterious glow, into the question of what woke up inside this ancient traveller, and why it happened where it did. The story, like many stories about the universe, begins with patience and careful observation. On the 1st of July 2025, the Atlas Survey Telescope in Chile detected something moving against the background stars. At first, there was nothing particularly remarkable about it, a faint point of light, one among thousands that astronomers track as they move through the inner solar system. But within days, as more telescopes turned their attention to this new object, something became clear. The trajectory was wrong, or perhaps not wrong, but different, hyperbolic. The mathematics of its path suggested it wasn't bound to the sun's gravity, it wasn't tracing any ellipse that would bring it back in thousands or millions of years. It was passing through, perhaps for the first and only time. This made it the third confirmed interstellar object humanity had detected visiting our solar system. The first, Oumuamua, arrived in 2017, moving so quickly through the inner solar system that we barely had time to point our best telescopes at it before it departed back into interstellar space. The second, Borisov, came in 2019, and behaved more like the comets we're familiar with, outgassing, developing a visible tail, following patterns that matched our models. But this new visitor, designated 3I Atlas, would prove to be something different again, something that would challenge certain assumptions about how interstellar objects behave, and perhaps about what chemistry exists in the galaxy beyond our small stellar neighbourhood. Through early July, 3I Atlas remained relatively quiet. Observers measured its trajectory, calculated its origin, somewhere in the direction of the constellation Canis Major, though of course it had been travelling for so long that any parent star it might have originated from had long since moved to a different part of the galaxy. They estimated its size, perhaps 23 kilometres across. Though such estimates carry uncertainty when you're trying to determine how much of the light you're seeing comes from reflected sunlight on a solid nucleus, versus how much comes from dust and gas surrounding it. The object was far from the Sun, 3.2 astronomical units away. That is, 3.2 times the distance between Earth and the Sun, roughly the same distance as the asteroid belt that orbits between Mars and Jupiter. At such distances, the Sun's warmth is gentle, diffuse. Comets from our own solar system, born in the cold outer regions, typically don't begin significant activity until they're much closer, inside Mars's orbit, where sunlight is strong enough to sublimate their surface ices with any vigour. But on August 8th, something changed. Astronomers at the MDM Observatory in Arizona, conducting a routine spectroscopic observation, detected something in the light coming from 3I Atlas that hadn't been there before. Not the simple reflected sunlight they'd been seeing, but emission, specific wavelengths of light that indicated the presence of molecules, specifically cyanogen, usually just called CN. It's a molecule that appears in cometary atmospheres when frozen ices containing carbon and nitrogen begin to sublimate, when the gentle pressure of sunlight provides enough energy to turn solid material directly into gas, skipping the liquid phase entirely. The presence of CN itself wasn't shocking. Comets often show CN emission as they approach the Sun, but the distance at which this was happening, that gave observers pause. At 3.2 astronomical units, 3I Atlas shouldn't have been active yet, or at least, not noticeably so. Solar system comets at similar distances are typically quiet, dormant, waiting for stronger sunlight before they begin to wake. Perhaps, the observers thought, this visitor from another star contained ices that were more volatile than what we're used to. Perhaps the chemistry formed around a different sun, created materials that respond to sunlight differently than the ices that condensed in our own solar system's formation. Or perhaps, and this is the possibility that makes you think a bit longer before sleep, perhaps there was something else providing energy to the object's interior, something beyond simple sunlight absorption. Over the next several nights, the team at MDM continued their observations, watching the CN emission strengthen gradually, predictably, as the object moved slowly inward. They measured the production rate of CN molecules, approximately 6 times 10 to the 24th power molecules per second. That's a number so large it becomes abstract. But imagine it this way: every second. Trillions upon trillions of cyanogen molecules were streaming away from the frozen nucleus, escaping into space, creating a tenuous atmosphere that extended perhaps thousands of kilometers in every direction around the solid core. Simultaneous observations in visible light showed something else. The coma, that cloud of gas and dust surrounding the nucleus, was growing. Not explosively, not dramatically, but steadily. The way things often grow in space, with the patience that vast distances and timescales demand. The measurement showed something called AEF rho, a parameter astronomers use to characterize how much dust a comet is producing, climbing to around 300 centimeters. Again, a number that might seem strange until you understand what it represents. a measure of the amount of sunlight being reflected by dust particles in the coma, scaled in a way that tells you about the dust production rate, regardless of how far away you're observing from. But it was the other emission lines that caught attention, particularly among those who study the exotic chemistry of objects from beyond our solar system. On August 21st, observations from the Very Large Telescope in Chile, using an instrument called X-Shooter that can measure light across a very broad range of wavelengths all at once, revealed something unusual. Not just CN, but also emission from neutral nickel atoms, Ni1 in spectroscopic notation. Specifically, numerous Ni1 lines across the optical spectrum, glowing against the backdrop of reflected sunlight and cometary dust. Metal atoms, glowing in space, around a comet. At first, this might seem normal. After all, comets do contain various elements, including metals, but the amount of nickel emission, and more importantly, the absence of iron emission that you'd typically expect to accompany it, suggested something different about how these atoms were being released from the nucleus. Iron and nickel often exist together in cosmic environments. Their neighbours on the periodic table form together in the hearts of dying stars, get incorporated into forming solar systems at similar rates. Yet here, nickel was streaming into space, while iron remained largely locked away. The researchers studying these observations proposed something intriguing. Perhaps the nickel wasn't sublimating directly from frozen ices or solid metal grains in the way we usually think about cometary outgassing. Perhaps it was being released through some lower energy process, what they termed photon-stimulated desorption, where ultraviolet light from the sun provides just enough energy to liberate atoms from the surface of dust grains, without requiring the high temperatures that melting or sublimation would demand. Or perhaps, more exotically, the nickel existed in the comet as part of metallated organic compounds, complex molecules where metal atoms are bonded into carbon-based structures, creating a kind of chemistry that we associate more with interstellar space than with solid objects. Think about that for a moment, as your thoughts begin to drift towards sleep. This visitor from another star might be carrying within it molecules that formed in very different conditions than the ices and rocks that make up comets born in our own solar system. Perhaps around its parent star, wherever and whatever that was, conditions existed that we haven't fully considered, different temperatures, different radiation environments, different timescales for chemical processes to occur. And those conditions got frozen into this object billions of years ago, preserved like a message in a bottle, waiting for the warmth of our sun to release them gradually back into space, where they could be seen, measured, and puzzled over by curious observers on a small planet that happened to lie along this traveller's path. The pattern of emission they were seeing suggested something else too. The nickel production rate and the CN production rate both seemed to scale with heliocentric distance in a particular way, changing as the object got closer to the sun, following a power law that was steeper than what you'd expect from simple sublimation of water ice. This suggested that whatever was driving the activity was responding strongly to even small changes in solar radiation, more strongly than water ice would. Perhaps carbon dioxide ice, which sublimes at lower temperatures than water, was the primary driver. Or perhaps carbon monoxide, even more volatile. Or perhaps, and this returns to that unsettling possibility, perhaps something else entirely was providing energy from within. As these observations accumulated through August, a picture began to emerge, though not a complete one. Never a complete one. That's not how astronomy works. You gather data, you make measurements, you see patterns, but the object itself remains distant, unreachable, knowable only through the ancient light it reflects and emits. You're always interpreting, always proposing explanations that might fit, knowing that tomorrow's observation might change the story. What observers could say with some confidence was this: 3i Atlas was active, in ways that seemed premature for its distance from the sun. It was releasing molecules, CN particularly, at rates that placed it at the lower end of activity for solar system comets, but still measurable, still significant. It was showing metal emission that suggested unusual chemistry, or unusual release mechanisms, and beneath all the measurements, beneath all the spectroscopic lines and photometric data points, There was that subtle rhythm, the way the light changed, gently, over the course of each 8-hour and 22-minute rotation period. Perhaps it was just the rotation itself, different parts of the nucleus presenting different surfaces to sunlight as the object tumbled slowly through space. Perhaps regions more rich in volatile ices would brighten as they faced the sun, then fade as they rotated into shadow. That would be the simple explanation, the one that requires no exotic physics, no unusual chemistry, nothing beyond what we already understand about how comets behave. But there was something about the consistency of it. The precision of that 8-hour, 22-minute period, that made some observers wonder. Not in the sense of seeing patterns where none exist, not in the sense of allowing imagination to override data, but in the sense that the universe is large and old, and has had time to do many things we haven't thought of yet. And when something travels through space for 9 billion years, when it potentially originates from a time in the galaxy's history that we call cosmic noon, that era of intense star formation, when the Milky Way was younger, more active, building up the thick disk of stars that orbit well above and below the flat plane where we reside, when something that old passes through our small corner of space and begins to glow at unexpected times. Maybe it's worth sitting with the mystery for a while, before reaching for simple answers. The observers certainly were. Night after night through August, telescopes around the world tracked this visitor. Some nights the seeing was poor, atmospheric turbulence blurring the images, making precise measurements difficult. Some nights, clouds intervened. Some nights the moon was too bright, flooding the sky with reflected sunlight that made faint emission lines harder to detect. But when conditions allowed, the observations continued, building up a picture of an object that was neither quite like the comets we know, nor quite like the first interstellar visitors we'd seen. By late August, as 3i Atlas moved inside 3 astronomical units, approaching the realm where solar system comets typically begin to show obvious activity, its glow had strengthened. The CN emission was now robust, easily detectable. The dust production was increasing, the coma was expanding. In some ways, it was starting to behave more like a familiar comet, following the patterns we'd expect. But that early activity, that premature awakening at 3.2 astronomical units, and that curious metal emission, those remained as quiet puzzles, as questions that would require more observations, more analysis, more careful thought. There's something appropriate, perhaps, about encountering mysteries as you prepare for sleep. The day's certainties give way to the mind's wandering, and in that wandering, there's often a kind of comfort. We don't need to solve everything immediately. We don't need to have final answers before we let our thoughts drift. The universe has been here for 13.8 billion years. These questions about an ancient traveller from another star can wait until morning. What matters, what allows sleep to come more easily, is perhaps just the knowing that such things exist. That out beyond our atmosphere, beyond the moon's gentle orbit, beyond Mars and the asteroid belt, something is moving that shouldn't be there, by the logic of our solar system's formation. Something that came from elsewhere, from elsewhen, carrying within it evidence of processes and chemistries that we're still learning to read. And that evidence is being released slowly, molecule by molecule, atom by atom, into the space between worlds, where it can be caught by telescopes and spectrographs, measured and pondered, added to the growing catalogue of things we know the universe can do. The astronomers studying 3i Atlas will continue their work. They'll track it through September, through October, as it reaches perihelion, its closest approach to the Sun, at just under 2 astronomical units, closer than Mars orbits, but still well outside Earth's path. They'll watch to see if the activity increases, if new molecules appear, if the metal emission continues or changes. They'll coordinate observations across multiple telescopes and wavelengths, building up the most complete picture possible of this visitor during its brief passage through our neighbourhood, and then, eventually, it will leave. Its hyperbolic trajectory will carry it back out beyond Neptune's orbit, beyond the Kuiper belt, beyond the heliopause, where the sun's influence fades into interstellar space. And once again, it will become what it was before, a dark, frozen traveller drifting between the stars, carrying its cargo of ancient ices and mysterious chemistry back into the galactic night. Perhaps in another 1,000,000 years, it will pass near another star, feel another sun's warmth, wake briefly once more, or perhaps not. Perhaps we were simply fortunate enough to be in the right place, at the right time in cosmic history, with telescopes powerful enough to catch this glimpse of what exists in the galaxy beyond our small stellar family. For now, let that thought settle with you, as your own thoughts begin to slow, as the need for sleep becomes more pressing than the need for answers. Somewhere in the space between Mars and Jupiter, an object that has travelled for billions of years is glowing, very faintly, releasing molecules and atoms into the vacuum, following a trajectory that was set long before our species existed. It will continue to glow through the night, whether we watch it or not. The measurements will still be there in the morning. The mystery will still be there, patient, as the universe itself. Rest now, knowing that the cosmos is vast and ancient and full of travellers bearing witness to regions and times we can only glimpse through their chemistry. Let the steady rhythm of your breathing match, perhaps, that gentle 8-hour and 22-minute rotation. Not literally, of course, but metaphorically, in the way that all rhythms in the universe somehow echo each other. The spin of a distant comet, the pulse of your heart, the patient turning of the galaxy itself, all following their appointed paths. Through space and time, the glow continues, the measurements accumulate, the story unfolds at its own pace, which is to say, slowly, carefully, with the thoroughness that good science demands, and that the universe, in its patience, allows. Tomorrow there will be more data, more observations, perhaps more questions. But tonight, there is only the soft darkness, the quiet hum of distant mysteries, and the gentle drift towards sleep that we all need, that we all eventually surrender to, whether we fully understand the universe or not. Sleep well. 3i Atlas, something started glowing inside it. Documentary for Sleep, Part 2, The Chemistry That Shouldn't Exist. As August gave way to September, and 3i Atlas continued its slow approach toward the inner solar system, astronomers prepared to turn humanity's most powerful infrared telescope toward this visitor from another star. The James Webb Space Telescope, floating at a point in space nearly 1,000,000 miles from Earth, where the gravitational pulls of our planet and the Sun balance in a delicate equilibrium, had been designed to peer into the deepest reaches of the universe, to capture the light of the first galaxies forming in the cosmic dawn. But it could also look closer, at objects passing through our own stellar neighbourhood, and reveal their chemical secrets in ways that ground-based telescopes, looking through Earth's thick atmosphere, sometimes cannot. The observation was scheduled for when 3i Atlas would be at approximately 2.9 astronomical units from the Sun, still well outside Earth's orbit, but closer than it had been during those first mysterious glimmerings in August. The telescope's infrared spectrograph, an instrument called near-spec, would split the faint infrared light coming from the comet into its component wavelengths, creating a spectrum that could be read like a chemical fingerprint. Different molecules absorb and emit light at specific wavelengths, and by measuring which wavelengths are present and which are missing, astronomers can determine what substances exist in a distant object without ever touching it, without ever sending a probe to collect samples. When the data arrived and was processed, when researchers began examining the spectral features emerging from the analysis, what they found was striking enough that the team spent several days checking and rechecking their measurements before preparing their report. The spectrum of 3i Atlas was dominated, absolutely dominated, by emission from carbon dioxide. Not just present, not just detectable, but overwhelming, the primary gas streaming away from the nucleus, far exceeding what they had expected to see. Comets, in the traditional understanding we've built from studying objects born in our own solar system, are sometimes called dirty snowballs. This phrase, while oversimplified, captures something essential about their composition. They're mixtures of water ice and rocky material, with various other frozen gases mixed in, Water is typically the most abundant volatile, the substance that sublimates most readily as a comet approaches the sun, creating the spectacular tails and glowing comas that have captured human imagination for millennia. Other ices are present: carbon monoxide, carbon dioxide, methane, ammonia, but usually in smaller quantities, as supporting players rather than the main character in the outgassing story. But 3I Atlas appeared to be different. The measurements from the James Webb Space Telescope suggested that carbon dioxide wasn't a minor component, but rather the dominant gas in the coma. The ratio between carbon dioxide and water, when the team calculated it, came out to approximately 16:1. That is, for every molecule of water vapour escaping the nucleus, 16 molecules of carbon dioxide were also making their way into space. This ratio wasn't just unusual, it was extraordinary. It was, in statistical terms, about 4.5 sigma above the trend line you'd draw if you plotted carbon dioxide to water ratios for long-period comets and Jupiter family comets as a function of their distance from the Sun. In the language of statistics, sigma measures how many standard deviations something is from the expected value. 1 sigma is within the normal range of variation. 2 sigma is notable. 3 sigma is where you start to pay real attention. 4.5 sigma is where you begin to ask if something fundamentally different is happening. Not impossible, not violating any laws of physics, but definitely outside the familiar patterns. Think about what this means as you settle deeper into whatever space you're occupying tonight. This visitor from another star, this fragment of some long-ago planetary system, is not just chemically different from comets we know in subtle ways. It's dramatically different in one of the most basic measurements we can make, the relative abundance of its primary volatile components. And this difference suggests, perhaps, that its formation environment was very different from the region of our own solar system. Where comets condensed from the swirling disk of gas and dust that surrounded the young sun, the researchers examining this data propose several possible explanations, each reaching toward understanding, each acknowledging the uncertainty that comes with trying to interpret the chemistry of an object whose origins are lost in the depths of space and time. One possibility involves radiation, not the gentle warmth of visible sunlight, but the harder, more energetic radiation that exists in various forms throughout the galaxy. Cosmic rays, ultraviolet light from nearby stars, the ambient radiation field that permeates interstellar space. If 3I Atlas spent billions of years drifting through regions of space where radiation levels were higher than what objects in our solar system's distant reaches experience, that radiation could have gradually altered the chemistry of its surface layers. Water ice, when bombarded by energetic particles over geological timescales, can be broken down, its hydrogen atoms knocked free, leaving behind oxygen that might combine with carbon to form carbon dioxide or carbon monoxide. This process, called radiolysis, happens slowly, molecule by molecule, but given enough time, and 3I Atlas potentially had billions of years, it could transform the surface composition of an icy body. Imagine the object drifting through the galaxy, cold and dark, far from any star's warmth. Perhaps it passed through regions where a nearby supernova had flooded space with high-energy particles. Perhaps it spent time in the dense environments near the galactic core, where radiation levels are higher than in the quieter spiral arms where our sun resides. Or perhaps it simply spent so long in interstellar space, accumulating the gradual effects of cosmic ray bombardment, that its surface chemistry shifted away from water-rich toward carbon dioxide-rich. This would be a story about time and patience, about how the universe can remake things given sufficient duration. The 3I Atlas we're seeing now might bear very little chemical resemblance to the object that first formed in its parent system. The surface layers at least could have been processed and reprocessed by radiation until the original composition was obscured beneath layers of altered ice, creating a chemical signature that reflects billions of years of journey, rather than the conditions of initial formation. But there's another possibility, one that reaches even further back, to the very birth of this object in whatever protoplanetary disk surrounded whatever star gave it form. In our own solar system's formation, there existed what astronomers call ice lines, specific distances from the young sun where different substances would have been cold enough to condense into solid form. The water ice line was relatively close in. The carbon dioxide ice line was farther out. The carbon monoxide ice line farther still. Objects that formed at different distances would have incorporated different mixtures of these ices based on what was frozen at their particular location in the disk. If 3I Atlas formed in its parent system's equivalent of the carbon dioxide ice line region, far enough from its star that carbon dioxide was frozen, but perhaps in a zone where water remained somewhat depleted, then its unusual chemistry might not be the result of billions of years of alteration, but rather the signature of its birthplace. This would make it a messenger not from interstellar space, but from a particular environment in a distant protoplanetary disk, carrying information about conditions that existed when that system was young, when planets were forming, when the architecture of that stellar family was being established. Both explanations have a kind of elegance to them, a way of making sense of the measurements without invoking anything exotic or unknown to physics. Radiation processing over time, or formation in a specific zone of a protoplanetary disk, either could produce an object rich in carbon dioxide, poor in water. The observations alone cannot tell us which story is true, or if perhaps some combination of both factors contributed to what we're seeing now. What the observations can tell us is that the galaxy contains, at minimum, one comet whose chemistry differs markedly from the comets born in our own system, and if one exists, how many others might be out there, drifting between the stars, each carrying its own unique chemical signature, each telling a slightly different story about formation conditions, radiation environments, and the long journey through interstellar space. The James Webb observations revealed more than just carbon dioxide, of course. The spectrum showed emission from water vapour, though in smaller quantities than the carbon dioxide. It showed carbon monoxide, another volatile that sublimates at very low temperatures. It showed something called OCS, carbonyl sulfide, a molecule containing carbon, oxygen and sulfur, something that appears in comets occasionally, but not commonly. And interestingly, the data showed evidence of water ice, not vapour, but solid ice particles in the coma, perhaps small grains that had been lifted from the surface by the outgassing, and were now reflecting and scattering light in characteristic ways. The presence of dust was confirmed as well, as expected from the earlier visible light observations. The coma glowed not just with the emission from gases, but with reflected sunlight from countless tiny particles, fragments of rock and organic materials. Perhaps some of that altered ice, all streaming away from the nucleus as the sunlight's gentle pressure and the sublimating gases pushed them outward. One detail that caught researchers' attention was the directionality of the outgassing. The emission wasn't uniform around the nucleus, but appeared enhanced in the sunward direction. That is, gases were streaming more vigorously from the side of the comet facing the sun than from the side in shadow. This makes sense, of course. Sunlight provides the energy for sublimation, so you'd expect the illuminated side to be more active. But the degree of asymmetry, the specific pattern of how the gas was distributed around the nucleus, provided clues about the surface properties, perhaps indicating that some regions were more volatile-rich than others, or that the insulating properties of surface dust varied across the nucleus. The researchers noted something else, something that speaks to just how unusual this carbon dioxide dominance was. They compared the 3I Atlas measurements to all the other comets that had been observed at similar distances from the Sun, looking at how carbon dioxide abundance typically relates to heliocentric distance. There's generally a trend. Comets closer to the Sun show different volatile ratios than those farther out, as different ices sublimate at different rates depending on temperature. But even accounting for its distance, 3I Atlas stood out as an outlier, sitting well above the trend line, in a category almost by itself. The only other comet in recent memory that showed comparably high carbon dioxide ratios was an object called C2016R2, which had its own peculiar chemistry for reasons that are still being studied. Perhaps then, 3I Atlas and objects like it represent a class of comets we simply haven't seen much of yet, a population of interstellar or distant origin objects whose formation conditions or radiation histories created chemical compositions quite different from the bulk of comets born in our solar system, As our detection methods improve, as we find more interstellar visitors, we might discover that the galaxy's cometary population is far more diverse than we've imagined, based solely on our local examples. Or perhaps, and this is worth considering as your mind drifts towards sleep, perhaps 3i Atlas is telling us something specific about its parent system, about the star it formed around, about the conditions in that distant proto-planetary disk. If carbon dioxide was unusually abundant there, if that system's ice chemistry was shifted toward carbon dioxide for some reason, maybe because of the star's particular type, or the disk's particular composition, or some event that happened during planet formation, then 3i Atlas carries that signature with it, a chemical memory of a place and time we can never directly observe, but can infer from this travelling messenger. The observations also revealed something about what might not be happening inside the comet. One possible explanation for anomalous activity in comets involves internal heat sources, perhaps radioactive decay of elements mixed into the nucleus, or perhaps residual heat from formation if the object was large enough to retain warmth for long periods. But the pattern of outgassing, the specific molecules being released, didn't strongly support the idea of significant internal heating. The activity seemed consistent with surface sublimation driven by sunlight, just with an unusual mix of volatiles doing the sublimating. This doesn't rule out internal processes entirely. The nucleus might have layers of different compositions, with the current outgassing reflecting whatever materials happen, to be on or near the surface at this moment. Perhaps deeper down, sealed beneath layers of dust or depleted ice, different chemistry awaits. Perhaps if we could somehow drill into 3i Atlas and extract a core sample, we'd find that the water-poor carbon dioxide-rich nature is only a surface phenomenon. But we can't do that. We can only watch from a distance and measure what the object chooses to release, as the sun's warmth gradually wakes it from its billions-year sleep. There's something almost dreamlike about the whole endeavour. This business of pointing our most sophisticated instruments at a frozen visitor from another star, and trying to deduce its history from the faint glow of molecules escaping into space. We're reading a message written in wavelengths of infrared light, in the presence or absence of specific spectral features. In ratios of one molecule to another, it's indirect, interpretive, always requiring careful thought about what else might produce the same observations. And yet, it works. The methods are sound, the physics is well understood. When photons of specific energies are absorbed or emitted by molecules, we can be confident about what molecules we're detecting. The uncertainty lies not in the measurements, but in the interpretation, in deciding which of multiple possible explanations best accounts for what we see, in acknowledging that we might be missing factors we haven't thought of yet. The team that analysed the James Webb data was careful to present their findings with appropriate tentativeness, using language like may indicate and is compatible with, and suggests the possibility that. This isn't hedging or uncertainty about the data itself. The measurements are quite precise. It's honest acknowledgement that when you're studying an object from another stellar system, when you're trying to understand processes that happened billions of years ago, or across vast gulfs of space, certainty is hard to come by. What you can offer is careful observation, rigorous analysis, and thoughtful consideration of what those observations might mean. And so, the picture of 3i Atlas that emerged from the infrared observations was of an object carrying unusual chemistry. Chemistry that might speak to radiation processing, or to formation conditions, or to some combination of factors we're still working to understand. An object releasing carbon dioxide as its primary volatile, with water playing a supporting role rather than the lead. An object that, in this chemical signature at least, stands apart from the comets born in our solar system, reminding us that the galaxy is vast and diverse, and capable of creating variations we haven't fully catalogued yet. As you drift closer to sleep now, let that image settle with you. A dark nucleus, perhaps 23 kilometers across, slowly rotating every 8 hours and 22 minutes, its surface warmed on one side by distant sunlight. Molecules of carbon dioxide and water and carbonyl sulfide and carbon monoxide streaming away into space, creating a tenuous atmosphere that glows faintly in infrared wavelengths, visible only to our most sensitive instruments. and within that nucleus, sealed in frozen depths, the record of wherever it came from, whatever star gave it birth, whatever radiation environments it passed through during its long journey. The chemistry shouldn't exist, not in the proportions we're seeing, not if this object formed like comets in our system formed, but it does exist, the measurements are clear, and so we adjust our understanding. We broaden our sense of what's possible in planetary system formation. We add 3i Atlas to the catalogue of known chemical diversity in the universe. The mystery is not that we don't understand it perfectly. The mystery would be, if we did, after seeing only one object, after measuring it for only a few months during its brief passage through our neighbourhood. Tomorrow, perhaps, there will be more data, more observations at different wavelengths. Perhaps someone will come up with a new model that explains the carbon dioxide dominance more completely, or that suggests tests we could perform to distinguish between the various hypotheses. But tonight, there is only the gentle acknowledgement that the universe is complex, that objects from other stars carry their own stories, and that sometimes those stories challenge our comfortable assumptions about how things should be. The comet continues its journey inward, continues its patient rotation, continues releasing its unusual chemistry into the space between worlds. The telescopes continue watching, continue measuring, continue building up the most complete picture possible. And somewhere in that intersection, between an ancient traveller and our moment in cosmic time, between what we can measure and what we can understand, the story of 3i Atlas slowly unfolds, one spectrum at a time. Rest now, knowing that the chemistry that shouldn't exist does exist, that the universe is full of such gentle contradictions, and that our role is simply to observe, to measure, to wonder, and to acknowledge that we're seeing only the smallest fraction of what's out there, waiting to be discovered. The carbon dioxide streams into space whether we understand why or not. The answer doesn't need to come tonight. Perhaps it never comes completely. Perhaps that's all right. Perhaps. The asking is enough. Sleep well. There's something almost poetic about the idea of metal glowing in the darkness of space. Atoms that were forged in the heart of a dying star, now streaming away from a frozen nucleus, catching sunlight and re-emitting it at specific wavelengths that can be measured by instruments on a distant world. When Dr. Rahat Gaonkar and his colleagues at the Very Large Telescope first detected those nickel emission lines in the spectrum of 3i Atlas, they were seeing something that doesn't happen often, or at least that we don't observe often in cometary atmospheres. Not because metal isn't present in comets, it certainly is, but because the process of getting metal atoms from the solid nucleus into the surrounding gas and getting them into a state where they emit light requires specific conditions that aren't always met. Let's drift slowly through this mystery, through what those glowing metal atoms might tell us about the interior of this visitor from another star, about the chemistry hiding beneath its surface, about processes that perhaps we're only beginning to understand fully. And as we move through these questions, let your mind relax into the rhythm of not knowing, the comfortable space where curiosity exists, without the pressure of immediate answers. Metal in space is, in one sense, everywhere. The heavier elements, iron, nickel, cobalt, and the rest, were created through nucleosynthesis in stellar cores, and scattered into the galaxy when massive stars ended their lives in supernovae. These atoms condensed into the next generation of stars and planetary systems, becoming part of the rocky material and dust grains that orbit young stars. Some of those atoms found their way into comets, mixed in with the ices, and organic materials, locked into solid grains of metal, or perhaps incorporated into more complex structures. When a comet approaches the sun and begins to warm, the ices sublimate. Water, carbon dioxide, carbon monoxide, and other volatiles turn from solid to gas and stream away from the nucleus. Dust particles, including particles containing metal, get entrained in these outflowing gases and carried into the coma. Usually, the metal remains locked in those dust grains, stable, not particularly reactive. You might detect metal in a comet's spectrum occasionally, but often it requires the comet to be quite active, quite close to the sun, or for something unusual to be happening. But 3i Atlas was showing metal emission, specifically nickel, at a distance where such emission wasn't particularly expected, and in quantities that seemed notable. The observations from late August revealed numerous emission lines from neutral nickel atoms, scattered throughout the optical spectrum. These weren't faint hints requiring careful analysis to confirm. They were robust features, clear signals that nickel atoms were present in the coma in significant numbers, and that they were being excited, given energy by sunlight, causing them to emit light at characteristic wavelengths. What made this particularly intriguing was what they didn't see. Iron, nickel's close cousin on the periodic table, was largely absent from the spectrum, or at least present in much smaller quantities than you might expect. In cosmic environments, iron and nickel typically occur together. They form together in stellar nucleosynthesis. They exist together in meteorites and asteroids. They're both common constituents of cosmic dust. If you're seeing abundant nickel, you generally expect to see abundant iron as well, but the spectrum of 3i Atlas showed strong nickel lines, with iron remaining quiet, subdued, barely detectable. This imbalance suggested something specific about how the metal was being released from the nucleus, about what physical or chemical processes were at work. If metal atoms were simply being liberated from dust grains through some generic heating or sublimation process, you'd expect iron and nickel to behave similarly, to appear in the spectrum in roughly proportional amounts. But they weren't behaving similarly. Nickel was streaming into space while iron stayed behind, and this differential behaviour pointed toward processes that could preferentially release one element over another. The researchers considering this puzzle proposed several mechanisms, each operating at different energy scales, each requiring different conditions. One possibility involved what's called photon-stimulated desorption, a process where ultraviolet photons from the sun strike dust grains in the coma and provide just enough energy to knock atoms loose from the grain surfaces, without requiring the high temperatures associated with evaporation or sublimation. It's a gentle process in a sense, working atom by atom, where the energy from individual photons breaks the bonds holding atoms to surfaces, allowing those atoms to drift away into the surrounding gas. If nickel atoms happen to be more loosely bound to dust grain surfaces than iron atoms, or if the specific wavelengths of ultraviolet light present in sunlight happen to match the energy needed to liberate nickel more efficiently than iron, then photon-stimulated desorption could explain the preferential release of nickel. This would be a story about surface chemistry, about the strength of bonds between metal atoms and whatever materials make up the surfaces of dust grains in 3i Atlas's coma. Another possibility involved chemistry that might seem exotic at first, but that exists in certain interstellar environments, metallated organic compounds. These are molecules where metal atoms are bonded directly into organic structures, creating hybrid molecules that are part metal, part carbon-based chemistry. In the diffuse gas between stars, in molecular clouds where new stars form, such molecules can exist, formed through slow chemical reactions in cold, dark environments, where atoms have billions of years to find each other and form unusual bonds. If 3i Atlas, during its long journey through interstellar space, accumulated or formed metallated organics on or near its surface, then the gentle warming from sunlight might be enough to break these molecules apart, releasing the metal atoms while leaving the organic components behind, or allowing them to sublimate separately. This process would operate at lower temperatures, require less energy, than simply evaporating metal from solid grains. And if nickel formed these organic compounds more readily than iron, or if nickel organic bonds were weaker than iron organic bonds, you could get preferential release of nickel. There's something almost beautiful about imagining such chemistry. Organic molecules with metal atoms woven into their structure, created perhaps in the cold depths between stars, now being gently taken apart by sunlight as the comet passes through the inner solar system. It's a reminder that chemistry in space can be far more diverse and complex than the simple picture of ices and rocks might suggest. Yet another possibility involved nickel-rich nanophases, extremely small particles or structures, perhaps just nanometers across, where nickel exists in forms that are more easily disrupted than bulk metal grains. At such small scales, surface effects dominate, A higher fraction of atoms are on the surface rather than in the interior, and surface atoms are generally more weakly bound, more reactive, more easily influenced by external energy sources like sunlight. If 3I Atlas contained dust with nickel-rich nanophases, perhaps formed through some process during the comet's history, then these nanophases might release nickel atoms more efficiently than larger metal grains would. The researchers even considered the possibility of nickel-carbonyl complexes, molecules where nickel atoms are bound to carbon monoxide. On Earth, nickel-carbonyl is created industrially and is highly toxic, but it forms relatively easily when nickel is exposed to carbon monoxide under certain conditions. In a comet rich in carbon monoxide, also with nickel-bearing dust, perhaps nickel-carbonyl forms on grain surfaces or in the spaces between grains. Then, as the comet approaches the Sun, the gentle warming might be enough to break these complexes apart, releasing both the nickel atoms and the carbon monoxide. This could explain both the nickel emission and potentially some of the carbon monoxide that had been detected in earlier observations. All of these mechanisms, photon-stimulated desorption, breakdown of metallated organics, disruption of nanophases, decomposition of carbonyl complexes, operate at what researchers call low activation energies. That is, they don't require the high temperatures that would be needed to simply evaporate metal from solid grains. This is important because 3I Atlas, at the distances where the nickel emission was first detected, wasn't particularly hot. The sunlight reaching it was diffuse, gentle. Any process releasing metal had to work efficiently at relatively low temperatures, had to be triggered by the modest energy available from distant sunlight. The fact that iron wasn't behaving the same way as nickel suggested that whatever mechanism was at work, it was somewhat selective, preferring nickel for reasons that might relate to bond strengths, or molecular formation rates, or surface binding energies, or some combination of factors that made nickel more easily liberated than iron. Under the specific conditions present in 3I Atlas's coma, perhaps most intriguingly, the researchers noted a potential connection between the nickel emission and the carbon monoxide that had been detected in the comet's spectrum. If nickel was being released through the decomposition of nickel-carbonyl complexes, then you'd expect the production rates of nickel and carbon monoxide to be correlated, that is, to vary together as conditions changed. Testing this hypothesis would require careful measurements over time, tracking how both species responded to changes in heliocentric distance, in solar radiation, in the comet's rotation and activity level. As you let these ideas settle with you, as your breathing slows and sleep draws nearer, consider the scales involved here. We're talking about atoms, individual nickel atoms, being released from grains or molecules, entering the surrounding gas, absorbing photons of sunlight, becoming excited, then releasing that energy as light at specific wavelengths that can travel across millions of kilometers of space, to be caught by telescopes and measured by spectrographs. Each photon detected represents a transaction, a story of energy and a matter interacting, of bonds breaking and forming, of atoms making journeys from solid surfaces into gaseous freedom. And we can read those stories, or at least begin to, by carefully analysing the wavelengths of light, by measuring how bright the emission is, by comparing what we see to laboratory measurements of how nickel behaves under various conditions. It's detective work at a distance, using light as evidence, using physics and chemistry as interpretive frameworks. The observations continued through late August and into early September, as 3I Atlas drew closer to the Sun. The team tracked how the nickel emission changed with heliocentric distance, looking for patterns that might distinguish between the various proposed mechanisms. They found that both the nickel production rate and the production rates of gases like cyanogen seemed to follow steep power laws with distance. That is, small changes in distance from the Sun produced relatively large changes in activity. This steep response suggested that whatever was driving the emission was sensitive to temperature or radiation intensity, changing rapidly as the comet's environment evolved. For production rates to scale so steeply with distance implies that the activation energy, the energy barrier that needs to be overcome for the process to occur, is relatively low, but not zero. High activation energy processes, like the evaporation of refractory materials, typically don't turn on until you're very close to the Sun. Low activation energy processes can operate farther out, but still respond strongly to increasing solar radiation. The behaviour of 3I Atlas's nickel emission fits somewhere in this regime of moderate but low activation energy, consistent with the proposed mechanisms of photon-stimulated desorption, or thermal breakdown of organometallic complexes. What we couldn't determine from the observations alone was exactly which mechanism was responsible, or whether perhaps multiple mechanisms were operating simultaneously, each contributing to the overall nickel emission in different proportions. This is often how it is in astronomy. You can constrain the possibilities, rule out scenarios that don't fit the data, identify mechanisms that are consistent with what you see. But pinning down the exact process with certainty requires more information than you have, or experiments you can't perform on an object that's millions of kilometers away, and moving at tens of kilometers per second. But that's all right. Progress in the understanding doesn't require instant, complete knowledge. It comes through accumulation of observations, through careful reasoning about what those observations imply, through the slow building of models that match the data better and better over time. The nickel emission from 3I Atlas was documented, measured, characterized. The various mechanisms were proposed, evaluated against what was known about cometary chemistry and grain surface physics. Future observations of this object or others like it might provide additional constraints, might allow researchers to distinguish more clearly between competing hypotheses. There's something comforting perhaps about acknowledging that we don't need to solve every mystery immediately, that the universe will wait patiently while we think things through, gather more data, refine our models. The metal atoms streaming from 3I Atlas aren't waiting for our understanding before they continue their journeys into space. They're following the physics and chemistry that governs their behaviour, indifferent to whether we've figured out all the details yet. As the observations accumulated, another aspect of the metal emission caught attention: the sheer efficiency with which nickel appeared to be released. The term used in the scientific literature was efficiently released gas phase nickel, meaning that the process, whatever it was, seemed quite good at getting nickel atoms from solid or complex states into the gaseous coma where they could be detected. This efficiency suggested that the mechanism wasn't rare or marginal, but rather a significant pathway for metal release under the conditions present at 3I Atlas. This has implications beyond just this one comet. If metallated organics, or nickel-carbonyl complexes, or photon-stimulated desorption from nanophases are efficient ways to release metal into cometary comas, then perhaps these processes are more common than we've realized. Perhaps they're operating in other comets, but not always detected because we haven't looked carefully enough, or because other factors dominate the spectrum. The interstellar nature of 3I Atlas might have made these processes more obvious, either because of the comet's particular composition, or because of how it's outgassing at the specific distances where we're observing it. The researchers who documented this emission were careful to note that their observations represented just a snapshot, a few weeks of data during one phase of the comet's approach to the Sun. As 3I Atlas continued inward, as it passed through perihelion and began its outbound journey, conditions would change. The temperature would rise or then fall, the solar radiation would intensify, then diminish. Different ices might begin to sublimate, the dust production might increase or decrease, and through all these changes, the nickel emission would likely evolve as well, perhaps becoming stronger, perhaps fading, perhaps changing its relationship to other species in the coma. Ideally, one would track the comet through its entire passage, measuring continuously, watching how every observable parameter changes with time and distance. But observing time on major telescopes is precious, allocated carefully among many competing projects. The window during which 3I Atlas would be well positioned for observation was limited, so astronomers made their measurements when they could, during the precious nights when telescope time was available, when weather cooperated, when the comet was bright enough and positioned favourably in the sky. What they captured was a glimpse, a detailed look at one moment in the comet's journey, enough to reveal that something interesting was happening with metal emission, enough to propose mechanisms and make predictions, enough to add this object to the catalogue of cometary behaviours we've documented. But it was also incomplete, partial, leaving questions for future observations, for other comets, for continued study of how metal interacts with ices and organics in these frozen travellers from other stars. And perhaps that's exactly as it should be. Each observation answers some question and raises new ones. Each discovery provides context for the next. The story of 3i Atlas isn't a story we'll finish telling in one observing campaign, with one set of instruments, from one perspective. It's a story that will be told in pieces by many observers over the months and years as the comet continues its path through our solar system and eventually back into interstellar space. For now, as sleep draws closer, as the day's thoughts finally begin to release their hold, let the image of those glowing metal atoms settle with you. Nickel, forged in stellar furnaces billions of years ago, incorporated into a comet in some distant planetary system, carried across the galaxy for unimaginable stretches of time, now being gently released by sunlight, glowing briefly in the darkness, visible to our instruments for this short window, before the comet passes on and the atom disperses into the vastness of space. They're still glowing out there now, as you drift towards sleep, still streaming away from that slowly rotating nucleus, still catching photons and emitting light, still following the physics that governs atomic behaviour. The telescopes might not be watching every moment, but the process continues regardless. The universe unfolds according to its own rhythms, and our role is simply to watch when we can, to measure what we're able, to think carefully about what those measurements mean. Rest now in the knowledge that such mysteries exist, that the cosmos is full of processes we're still learning to understand, and that somewhere between the atoms streaming into space and the instruments catching their light, human curiosity creates meaning, creates story, creates the slow accumulation of knowledge. That is perhaps our species' most persistent characteristic. The metal glows, we watch, we wonder, and that gentle wondering is perhaps enough to carry us peacefully into whatever dreams may come. Sleep well, knowing that the universe continues its patient work, atom by atom, photon by photon, whether we're watching or not. There's a particular kind of vertigo that comes from contemplating deep time, from trying to wrap your mind around numbers so large that they lose their immediate meaning and become instead a kind of abstract immensity. 9 billion years. Not 9,000. Not 9 million. But 9 billion. A span of time so vast that it contains within it the entire history of Earth's complex life, repeated twice over, with room to spare. And 3i Atlas, this frozen visitor now glowing gently in the space between Mars and Jupiter, may have been travelling through the galaxy for exactly that long, perhaps longer, carrying within its icy depths the chemical signature of an era in cosmic history that we call, somewhat poetically, cosmic noon. Let your mind drift now, as we trace backward through time, as we follow the trajectory of this ancient traveller, not just through space, but through the deep currents of galactic history. This is a story measured not in years or centuries, but in the rise and fall of stellar generations, in the slow evolution of the Milky Way itself, from a younger, more chaotic structure, into the grand spiral we observe today. When astronomers first calculated the trajectory of 3i Atlas with sufficient precision to determine where it came from, or at least what direction it was travelling from, they found something intriguing. The object's velocity relative to the local standard of rest, that is, relative to the average motion of stars in our neighbourhood of the galaxy, was approximately 58 kilometers per second. This might not sound extraordinary at first. Space is vast, and objects move quickly through it. But the specific velocity, and more importantly the direction of that velocity, told a story about the comet's origins. Our Sun, along with most of the stars visible in the night sky, belongs to what's called the thin disk of the Milky Way, a relatively flat distribution of younger stars, typically less than 10 billion years old, orbiting in roughly circular paths around the galactic centre. These stars, our Sun included, move in an orderly fashion, like traffic on a circular highway, with velocities that are fairly similar to each other. Objects born in this population tend to have velocities that reflect this orderly motion, but the galaxy contains other populations of stars as well. above and below the thin disk, extending several thousand light-years perpendicular to the galactic plane, exists what's called the thick disk, a population of older stars, typically 9 to 13 billion years old, with more random, less circular orbits. These stars were born during an earlier era in the galaxy's history, a time of more active star formation, when the Milky Way was still settling into its current structure, and their velocities reflect this older, more chaotic origin. They move faster relative to the thin disk, with motions that are less orderly, more inclined, carrying the kinematic signature of the galaxy's youth. When researchers analysed the velocity of 3I Atlas, they found that it matched quite well with what you'd expect from a thick disk object. Not perfectly. There's always uncertainty in these measurements, always the possibility that what looks like a thick disk velocity could have other explanations. But the match was good enough to be suggestive, to raise the possibility that this comet originated not from a star similar to our Sun, not from a young stellar system in the thin disk, but rather from an older system, formed during that era of intense star formation 9 to 13 billion years ago, when the galaxy was younger, when stars were being born at rates far exceeding what we see today. If this is true, and we must always hold such conclusions tentatively, acknowledging the uncertainties, then 3I Atlas is not just an interstellar visitor, but a time traveller of sorts, a messenger from cosmic noon, carrying frozen evidence of conditions that existed when the universe was less than a third of its current age. Think about what that means as you settle deeper into rest. This object, this chunk of ice and rock and complex chemistry, condensed from a protoplanetary disk orbiting a star that formed when the cosmos was young. Perhaps that star was more massive than our Sun, burning brightly and briefly before ending its life and scattering heavy elements into space. Or perhaps it was a star much like ours, still burning today somewhere in the galaxy, unknowingly having lost a small piece of its planetary system to the depths of interstellar space. Billions of years ago, however it began, at some point in the distant past, 3I Atlas was ejected from its parent system. Perhaps gravitational interactions with a forming planet kicked it outward, past the equivalent of that system's Kuiper belt, past whatever boundary separated the star's gravitational dominance from the freedom of interstellar space. Or perhaps it was always on the edge, formed in the outer reaches of the disk, barely bound, requiring only a gentle nudge from a passing star or a slight perturbation from the galactic tide to send it drifting away. And once freed, it began a journey that would span the galaxy. Not directly. Nothing in the galaxy moves in straight lines for long. Everything is subject to gravity, to the collective pull of billions of stars, to the gravitational potential of the galactic disk itself. So, 3I Atlas would have followed an orbit of sorts. Though nothing like the neat ellipses of planets around stars, it would have traced a path that took it above and below the galactic plane, passing through regions of varying stellar density, through the thin disk and thick disk, perhaps even venturing into the galactic halo where the oldest stars reside. During this journey, which may have lasted 9 billion years or perhaps somewhat less, the comet would have experienced many things. It would have passed through molecular clouds, vast regions of cold gas and dust where stars form, where the density of material is higher than in typical interstellar space. The drag from that gas, slight as it was, would have affected the comet's trajectory over such vast timescales. The radiation from nearby stars would have gradually processed its surface, breaking down molecules, creating new chemistry, perhaps depleting water and enriching carbon dioxide in the ways we discussed earlier. It might have passed relatively close to other stars, not close enough to be captured into an orbit, but close enough to feel their gravitational influence, to have its path bent slightly, accumulated over many such encounters into a trajectory that eventually, after billions of years of wandering, happened to intersect with our solar system. The odds of any particular interstellar object encountering any particular star system are vanishingly small, but the galaxy is vast, contains hundreds of billions of stars, and time is long. Given enough objects wandering between the stars, given enough time for those wanderings to unfold, occasional encounters become inevitable. Perhaps the most humbling aspect of this timeline is how recently we entered the story. Earth formed about 4.5 billion years ago. If 3i Atlas is indeed 9 billion years old, then it was already ancient when our planet condensed from the solar nebula, already well into its journey through the galaxy when the first oceans appeared on Earth's surface, when the first life emerged, when photosynthesis began producing oxygen, when complex life evolved, when animals colonized the land, when dinosaurs rose and fell, when our own species appeared and began looking up at the stars, wondering what else might be out there. All of human history, all of recorded civilization, occupies perhaps the last 10,000 years. A span of time that is to the comet's journey roughly what a single heartbeat is to a human lifetime. We are catching the briefest glimpse of an object whose existence stretches across timescales that dwarf anything in human experience, anything in the experience of life on Earth, anything except the cosmos itself. As you drift closer to sleep, let that perspective settle with you. Not as something that makes human concerns trivial, but as something that connects us to the vastness of time and space, that reminds us we're part of something far larger and older than our immediate experience suggests. The comet's journey, and our moment of observing it, are connected by chance, by the slow unfolding of orbital mechanics and galactic dynamics, by the patient accumulation of improbabilities that eventually inevitably becomes reality. The calculation of the comet's age relies on several pieces of evidence beyond just its velocity. Astronomers look at its trajectory, trace it backward through time using models of the galaxy's gravitational potential, and ask where such an orbit would have originated. They consider the comet's chemistry. Does it match what we'd expect from objects formed during different eras of galactic history? They examine how weathered the surface appears, how processed by radiation, though such evidence is indirect and must be interpreted carefully. The thick disk assignment, the suggestion that this object comes from cosmic noon, is based on the balance of these different lines of evidence. It's not certain. Few things in astronomy are when you're working with single objects and limited data, but it's consistent, plausible, more likely perhaps than alternatives that would require more special circumstances or more unusual explanations. If we accept this timeline, even provisionally, then we can sketch a rough history. 9 to 13 billion years ago, during an era when the universe was between 1 and 4 billion years old, a star formed in what would become our Milky Way galaxy. This star, wherever it was, whatever its properties, was surrounded by a disk of gas and dust, as young stars typically are. Within that disk, materials condensed, agglomerated, formed into larger bodies. Most of that material went into planets or remained in stable orbit around the star, but some fraction, perhaps a significant fraction, was ejected, thrown outward by gravitational interactions into the space between stars. One of those ejected objects, perhaps no more remarkable than thousands or millions of others that suffered the same fate, became what we now call 3i Atlas. It drifted, slowly at first, then faster as it left the star's gravitational embrace entirely. Its surface, initially perhaps warm from formation, cooled to the ambient temperature of interstellar space, a few degrees above absolute zero. Its chemistry, whatever it had been when it formed, began the long, slow process of alteration by cosmic rays, by ultraviolet light from distant stars, by the occasional passage through denser regions of the interstellar medium. Billions of years passed. The object traced a complex path through the galaxy, responding to gravitational influences it encountered, moving generally in the way that thick disk objects move, with higher velocity, more inclined orbit, less circular motion than the younger stars and objects that populate the thin disk. It was one fragment among countless others, most of which we'll never detect, drifting through the spaces between stars, occasionally coming close enough to stellar systems to feel their gravity, but not close enough to be captured, to be seen, to be measured. And then, recently in cosmic terms, does its path happen to intersect with our solar system? Perhaps there was nothing special about this intersection. It might have passed close to other stars during its journey, without being noticed, without anyone present to observe. But this time it encountered a system containing a technological species, with telescopes and spectrographs, with the ability and curiosity to notice unusual objects passing through, to measure them, to wonder about their origins. The velocity with which 3i Atlas entered the solar system, at 58 kilometers per second relative to our local frame of reference, is fast by everyday standards, but not particularly unusual for objects in the thick disk population. What made it notable was that this velocity was added to the Sun's own orbital motion around the galaxy, resulting in a trajectory relative to the Sun that was hyperbolic, unbound, destined to pass through once and then leave, returning to the interstellar medium from which it came. There's something almost poignant about this temporary encounter. The comet has been travelling for billions of years, through countless cubic light years of galactic space, through regions we can barely imagine, past stars that may no longer exist, through clouds of gas that have since formed new stellar generations. And now, for just a few months, it passes through our small corner of the galaxy, close enough to our Sun to warm slightly, to begin outgassing, to glow in ways we can detect and measure. Soon, on cosmic timescales, it will leave. Its trajectory will carry it past perihelion, past Mars's orbit outbound, past Jupiter and Saturn and Neptune, past the heliopause where the solar wind gives way to the interstellar medium. And then, it will once again be what it was before, a dark, frozen wanderer, indistinguishable from the countless other objects drifting through the spaces between stars, invisible except for those rare moments when it happens to pass through another stellar system and briefly wakes to the warmth of another sun. Perhaps this has happened before. Perhaps during its 9 billion-year journey, 3i Atlas has passed through other solar systems, has felt the warmth of other stars, has outgassed briefly before returning to dormancy. We have no way to know. The object carries no record of such encounters that we can read, no diary of its wanderings, only the chemistry frozen into its structure, and the trajectory it follows now. Or perhaps we're the first. Perhaps in all those billions of years, this is the first time the comet has encountered a star closely enough to wake, the first time its chemistry has been analysed, the first time anyone has wondered about its origins and journey. That seems less likely, given the timescales involved, but it's possible. The galaxy is vast, but also empty on small scales. The average distance between stars is several light years, and the cross-section of a stellar system is tiny compared to the volume of space. Most of the comet's journey was likely spent in the deep cold between stars, far from anything that would warm it, or perturb its orbit significantly. As sleep draws nearer, as the weight of billions of years presses gently on your imagination, perhaps there's something comforting in the steadiness of it all. The comet didn't rush through its journey. It didn't need to arrive anywhere by any particular time. It simply moved, following the laws of motion and gravitation, patient as only something without consciousness can be patient, carrying its frozen cargo through the turning of galactic seasons. And we, brief as our species is in cosmic terms, happened to be here when it passed. We happen to have developed, in just the last few decades, the instruments sensitive enough to detect it, to measure its chemistry, to recognise it as something not from our solar system. We happen to be curious enough to look, careful enough to measure, thoughtful enough to wonder about what those measurements might mean. This intersection of the comet's ancient journey and our moment of technological capability is pure chance, but it's the kind of chance that becomes inevitable given enough time. Somewhere in the galaxy, intelligent species are probably observing their own interstellar visitors, running their own spectrographs, proposing their own theories about chemistry and origin. And elsewhere, other interstellar objects pass through other systems unobserved, unwondered about, their chemistry and history remaining unknown to anyone. We're fortunate, perhaps, to live in this moment when we can participate in this cosmic observation, when we can add our small piece to the universe's understanding of itself, because that's what we're doing in a sense. We're the universe becoming conscious of its own history, its own processes, its own deep patterns, the atoms in our bodies, the thoughts arising in our minds, the curiosity that drives us to point telescopes at ancient travellers. All of this is the cosmos examining itself, wondering about its own nature. The comet continues its journey, indifferent to our observations, following its trajectory as it has for billions of years. Tomorrow it will be slightly closer to the sun, slightly warmer, slightly more active perhaps, and we'll continue measuring, continue analysing, continue building our understanding piece by piece. But tonight, there's only the gentle awareness of deep time, of journeys that span the galaxy, of frozen chemistry carrying messages from cosmic noon. Rest now, knowing that the universe is patient, that time flows at its own pace, that 9 billion years is long enough for almost anything to happen, and yet brief compared to the cosmos's total age. Let the thought of that ancient traveller, glowing faintly in the darkness between worlds, carry you gently into sleep, where time becomes fluid and distance becomes meaningless, where the mind can wander as freely as comets through the galaxy, unbounded by the concerns of waking life. The journey continues, the universe turns, the comet drifts toward perihelion and beyond, and we, having glimpsed it briefly, return to our own smaller timescales, our daily rhythms, our human concerns, enriched perhaps by this reminder of how vast and old and patient the cosmos truly is. Sleep well, knowing that somewhere in the space between Mars and Jupiter, a traveller from cosmic noon continues its ancient journey, glowing gently, releasing molecules and atoms formed around another star in another era, visible to us for this brief moment before it passes on into the darkness from which it came. There's something extraordinary about coincidence, about the way unrelated events sometimes align in ways that create opportunities no one planned for. When the National Aeronautics and Space Administration launched the Psyche spacecraft in October of the year 2023, its mission was straightforward: travel to a metal-rich asteroid orbiting between Mars and Jupiter, study its composition, test theories about planetary cores and the building blocks of rocky worlds. The mission planners had calculated the trajectory years in advance, plotted the path that would carry Psyche through the inner solar system on its way to its distant target. They couldn't have known that 2 years later, as their spacecraft sailed through the space between worlds, an ancient visitor from another star would happen to pass nearby, close enough for an unplanned encounter that would become one of the most significant observations in the history of interstellar studies. Let your thoughts drift now toward September, toward those early autumn days when the trajectory of 3i Atlas and the trajectory of humanity's metal-seeking probe converged in the darkness between Mars and Earth. This is a story about preparation meeting opportunity, about how sometimes the universe offers gifts we didn't know to ask for, about what it means to witness something no human has witnessed before, a spacecraft from Earth passing within measurable distance of an object from another star. The realization came relatively early, within weeks of the 3i Atlas's discovery in July. Orbital dynamicists, tracking both the comet's trajectory and the positions of various spacecraft scattered throughout the solar system, noticed that the paths would intersect, or nearly so, not collide. Space is vast, and such encounters are carefully avoided, but pass close enough that Psyche's instruments, designed to study a metal asteroid, might be able to turn toward the comet and capture data that Earth-based telescopes, separated from the comet by over 100 million kilometers, could never obtain. The closest approach was calculated for September 4th, 2025. On that date, Psyche would pass within 0.302 astronomical units of 3i Atlas, about 45 million kilometers, roughly a third of the distance between Earth and the Sun. In cosmic terms, this is remarkably close. Close enough that even though Psyche wasn't designed for cometary observations, even though its instruments were optimized for studying metal and rock rather than ice and gas, it could still gather valuable data. Images at higher resolution than any telescope could provide from Earth. Spectra captured from a different angle, a different perspective. Perhaps thermal measurements, dust density readings, anything the spacecraft's sensors could detect as it sailed past. The opportunity was unprecedented. In 2017, when Oumuamua became the first confirmed interstellar object detected passing through our solar system, it moved so quickly and was discovered so late that no spacecraft was in position to observe it closely. It was gone before we could fully appreciate what we were seeing. before we could mount any kind of coordinated observation beyond pointing telescopes at its rapidly receding form. When Borisov arrived in 2019, we had more warning, more time to study it, but again, no spacecraft happened to be positioned favourably. We watched from Earth and from Earth orbit, but the comet remained distant, knowable only through the ancient light it reflected and emitted. But 3i Atlas was different. By chance, by pure cosmic coincidence, multiple spacecraft would pass relatively near the comet during its passage through the inner solar system. Not just Psyche, but also the fleet of orbiters and landers at Mars, spacecraft from the National Aeronautics and Space Administration, the European Space Agency, India, China, the United Arab Emirates, all positioned in their various orbits when 3i Atlas would pass closest to the red planet on October 3rd. And farther out, the JUICE spacecraft, on its long journey to Jupiter's moons, would encounter the comet's tail in early November, potentially passing through the stream of dust and gas that 3i Atlas was shedding as it moved. Each encounter offered something unique. Psyche's passage in early September would catch the comet while it was still approaching perihelion, still brightening, still in that phase of gradually increasing activity that observers on Earth had been tracking since August. The Mars observations in early October would occur when the comet was even closer to the Sun, warmer, potentially more active, allowing the Martian orbiters to measure the coma from a perspective that ground-based telescopes could never achieve, from above, looking down on the comet as it passed below the orbital plane where most of the Martian spacecraft reside. And the JUICE encounters, if it indeed passed through the tail as predicted, would offer something extraordinary. Direct sampling of material ejected from an interstellar object. JUICE wasn't designed with this mission in mind. It didn't carry instruments specifically meant to analyze cometary dust, but it had sensors that could detect particles, measure their impacts, perhaps determine something about their composition and properties. It would be the closest thing to a sample return mission that we could hope for, without having years of advance notice to plan a dedicated mission. The implications of these encounters extended beyond just the immediate science. For years, researchers studying the possibility of life beyond Earth, the search for techno-signatures, the question of whether intelligence exists elsewhere in the universe, had discussed interstellar objects as potential targets for such searches. Not because anyone seriously expected an interstellar comet to be artificial, not because there was any reason to think 3i Atlas was anything other than a natural remnant of planet formation in some distant system, but because the methodology was important to develop, the frameworks for how you'd examine such an object, what you'd look for, what observations might distinguish between natural and artificial origins. The discussion had been theoretical until now. Oumuamua had sparked intense speculation, particularly because of its elongated shape and the slight acceleration it exhibited, one that was difficult to explain with conventional cometary outgassing. Some researchers proposed, cautiously and with many caveats, that its properties might warrant consideration of artificial origins, not because the evidence demanded it, but because the evidence didn't completely rule it out, and because developing the methodological tools for making such assessments was important, regardless of whether that particular object warranted them. 3i Atlas, with its more conventional cometary behaviour, with its obvious outgassing and chemical signatures that match natural processes, didn't inspire the same level of speculation. But the multiple spacecraft encounters, the opportunity to observe an interstellar object from multiple perspectives with multiple instrument types, represented a valuable test case for how humanity might study future interstellar visitors, including hypothetical ones that might show more ambiguous characteristics. The teams operating various spacecraft began coordinating their observations months in advance. Psyche's mission planners calculated what maneuvers, if any, would be needed to optimize the spacecraft's pointing during the encounter. The Mars orbiter teams planned observation sequences, deciding which instruments to activate, what measurements to prioritize, given the limited time window when 3i Atlas would be within range. Everyone was operating under constraints. Spacecraft have limited power, limited data storage, limited bandwidth to transmit information back to Earth. Every observation of the comet meant not observing something else, not collecting data on the spacecraft's primary mission targets. But the opportunity was too significant to pass up. The consensus emerged quickly. This was worth doing. worth the diversion of resources, worth the risk of missing other observations. An interstellar object passing close enough to spacecraft that we could study it directly is not something that happens often. Given the rarity of interstellar visitors and the vastness of space, it might be decades or longer before another such opportunity arose. If there were technical or logistical problems, if something didn't work as planned, there would be no second chance, no opportunity to try again next year. As September approached, as Psyche continued its steady progress through space on its journey toward the metal asteroid that was still years away, the teams prepared. Software updates were uploaded to ensure the spacecraft's instruments would operate optimally during the encounter. Communication schedules were adjusted to maximize the data that could be transmitted back to Earth in the hours and days following the closest approach. Scientists on Earth prepared their analysis tools, ready to examine whatever data the spacecraft managed to collect, and then, on September 4th, the encounter occurred. Not dramatically. There were no explosions, no close calls, nothing that would make for exciting footage, just a spacecraft moving along its predetermined path, its instruments turned toward a distant glowing speck, capturing photons, recording measurements, storing data in its memory banks for later transmission home. From Psyche's perspective, if a spacecraft could be said to have perspective, 3i Atlas was just another object in space, no different in principle from the thousands of asteroids and comets that populate the solar system. But from our perspective, from Earth, where we waited for the data to arrive, it was extraordinary. The closest any human-made instrument had ever come to an object from another star. The data, when it began arriving over the subsequent days and weeks, revealed what close-up observations can offer that distant ones cannot. Higher resolution images, showing structure in the coma, variations in brightness and density that might indicate jets or active regions on the nucleus. Spectra captured from a different viewing angle, potentially showing different chemistry than Earth-based observers had detected. Measurements of how the dust scattered light, providing clues about particle sizes and compositions. Perhaps most valuable was simply the different perspective, the way that observing from multiple locations simultaneously allowed researchers to build up a three-dimensional picture of the comet's structure and activity. Earth-based telescopes saw 3i Atlas from one direction. Psyche saw it from another. The Mars spacecraft, when they made their observations a month later, saw it from yet another angle. Combining these viewpoints created a more complete understanding than any single observatory could provide. The Mars encounters in early October offered their own insights. Several orbiters, positioned in their various paths around the red planet, turned their cameras and spectrometers toward 3i Atlas as it passed through the region of space near Mars's orbit. The observations were brief, the comet was moving quickly, and the spacecraft had to balance their interstellar visitor studies with their ongoing missions to explore Mars itself. But even brief observations from close range can reveal details that extended observations from great distances cannot. The images captured by the Mars orbiters showed the comet's coma in greater detail than had been visible from Earth, revealing structure, perhaps spiral patterns indicating rotating jets, variations in brightness that might correspond to different regions of the nucleus becoming active as they rotated into sunlight. The spectroscopic observations added to the growing database of the comet's chemistry, confirming earlier measurements while potentially revealing additional species that had been too faint to detect from farther away. And then, in early November, came perhaps the most unusual aspect of the entire encounter sequence. JUICE's passage through the predicted location of 3i Atlas's dust tail. The spacecraft, launched in 2023 on its long journey to explore Jupiter's icy moons, happened to be positioned such that the thin stream of dust particles trailing behind the comet would intersect its path. It wasn't a dense encounter. Cometary tails are extraordinarily tenuous, containing only a few particles per cubic kilometre in most regions. But even detecting a few impacts, even measuring a slight increase in the dust environment as the spacecraft passed through the tail region, would confirm models of how the dust was distributed and provide direct physical evidence of material ejected from an interstellar object. The spacecraft's instruments, designed primarily for studying Jupiter's radiation environment and ice-rich moons, nevertheless included sensors capable of detecting dust particles. As JUICE passed through the predicted tail location, those sensors recorded what they encountered, adding another piece to the mosaic of observations building up around 3i Atlas. There's something almost poetic about this collection of encounters, about the way humanity's scattered spacecraft, each launched for entirely different purposes, each following its own mission, all happened to be positioned favourably when this ancient visitor passed through. We didn't plan for this. We couldn't have. The decisions to launch these spacecraft were made years ago, when 3i Atlas was still far beyond the heliopause, approaching the solar system undetected, unknown. But the solar system is full of our machines now, full of orbiting instruments and travelling probes, and that presence meant that when an interstellar visitor arrived, we were positioned by chance to study it more closely than we ever could have otherwise. This is perhaps a preview of how the future will unfold. As our presence in space grows, as more spacecraft travel to more destinations, as we build up infrastructure beyond Earth, future interstellar visitors will increasingly encounter a solar system that is not empty but populated, not silent but listening, not unprepared but ready to observe whatever the universe sends our way. 3i Atlas might be the first interstellar object we've studied with spacecraft, but it will not be the last. As sleep draws closer, as the day's final thoughts begin to release their hold, let this image settle with you. A network of human instruments scattered through the solar system, each doing its own work, studying its own targets, but all connected by the shared goal of understanding the cosmos. And when something unexpected passes through, when the universe offers an opportunity we didn't specifically plan for, those instruments turn, measure, record, adding to our collective knowledge of what exists beyond our stellar neighbourhood. The spacecraft continue their missions now, their brief observations of 3i Atlas complete, their data transmitted back to Earth, where it will be analysed, published and folded into models and theories about interstellar objects, planetary system formation, and the vast diversity of chemistry that exists across the galaxy. The comet continues its journey toward perihelion and beyond, its moment of close observation passing, its slow fade back into interstellar darkness beginning. Sleep well, knowing that even now, somewhere in the depths beyond Mars, an ancient traveller continues its long voyage home, but for those few weeks in September and October and November of 2025, humanity and an ancient traveller from cosmic noon shared a moment of connection, a convergence of trajectories in the darkness between worlds. We reached out with our instrument, with our curiosity, with our desire to understand, and the universe, through this frozen messenger, reached back, offering glimpses of chemistry and physics and history that exist beyond our small corner of space. Rest now in the knowledge that our species, brief as we are in cosmic terms, has developed the tools and the curiosity to study such visitors, to learn from them, to add their stories to our understanding of the galaxy we inhabit. The spacecraft float onward through the dark. The comet glows faintly in the space between Mars and the Sun, and we, having witnessed something remarkable, return to our own rhythms, our human scale, our daily concerns, enriched by the awareness that we live in an era when such encounters can be documented, measured, understood. Sleep well, knowing that somewhere in space, instruments we built continue their patient work, watching, measuring, recording, slowly building up the archive of observations that represents humanity's contribution to the universe's understanding of itself. As we drift toward the end of this journey through the story of 3i Atlas, as the need for sleep becomes more pressing than the need for answers, let's settle into one final set of observations. One more perspective on this. Visitor from another star. In mid-August, while ground-based telescopes were tracking the comet's growing activity, while the Very Large Telescope was detecting those mysterious nickel emissions, another instrument turned its attention toward the ancient traveller, an instrument designed not for individual objects but for surveying the entire sky, for mapping the cosmos in infrared wavelengths, where much of the universe's story is written in light invisible to human eyes. Sphere-X, the spectrophotometer for the history of the universe, Epoch of Ionization, and ICE's Explorer, had been placed in Earth orbit to study the large-scale structure of the cosmos, to map hundreds of millions of galaxies, to search for water ice in stellar nurseries. But like all survey instruments, it could also be directed towards specific targets of interest, toward objects that might reveal something particular and valuable about cosmic chemistry. And 3I Atlas, with its unusual composition and interstellar origin, certainly qualified as such a target. The observations conducted when the comet was approximately 3 astronomical units from the Sun captured something that complemented the James Webb Space Telescope's findings, while adding new details to the picture. The Spherex data, spanning wavelengths from 3/4 of a micrometer to 5 micrometers, from near-infrared into mid-infrared, revealed absorption features indicating the presence of water ice. Not water vapor, which had already been detected, but solid ice crystals, particles perhaps lifted from the surface by outgassing, now suspended in the coma, scattering and absorbing light in characteristic patterns. The presence of water ice alongside the strong carbon dioxide emission created an interesting puzzle. The James Webb observations had shown that carbon dioxide dominated the gas phase, far exceeding water vapor. But the Spherex data suggested that water ice was abundant in the solid particles making up the dust component of the coma. This could mean several things. Perhaps the nucleus surface was layered, with different regions having different ice compositions. Perhaps the water, being less volatile than carbon dioxide at the temperatures the comet was experiencing, remained largely frozen in dust particles, while carbon dioxide sublimated directly into gas. Or perhaps the interior structure of the nucleus created conditions where carbon dioxide could escape more easily than water, leaving behind water-rich dust. Whatever the explanation, the observations reinforced the picture of 3I Atlas as a chemically complex object, not uniform but varied, with different components behaving differently as the gentle warmth of sunlight reached the frozen nucleus. The Spherex observations also confirmed and extended the measurements of the carbon dioxide coma. The infrared images resolved the coma spatially, showing that it extended approximately 3 arc-minutes across the sky, a measurement that, at the comet's distance, corresponded to a physical size of several 100,000 kilometers. Not the tenuous whisper of gas immediately around the nucleus, but a vast cloud, expanding slowly as molecules and atoms escaped the comet's weak gravity and dispersed into surrounding space. The production rate calculated from these observations was substantial, approximately 9 times 10 to the 26th molecules per second streaming away from the nucleus. That's a number almost impossible to visualize meaningfully. Every second, nearly a billion molecules of carbon dioxide were being released into space. Over the course of a day, the mass loss from just carbon dioxide alone would amount to thousands of tons, and this was happening at a distance where many comets from our solar system would still be essentially dormant, not yet active enough to detect easily. The observations also allowed researchers to place limits on other species. The production rate of water vapor, if it was being released at all at detectable levels, appeared to be several times lower than the carbon dioxide production rate, confirming the unusual gas ratio that the James Webb Telescope had measured. Carbon monoxide, another volatile that can sublimate far from the Sun, was present, but not at levels that dominated the spectrum. One detail that emerged from careful analysis of the Spherex images was the absence of obvious structures, no clear jets, no prominent trails or tails in the images, just a relatively smooth, expanding coma. This could mean that the outgassing was fairly uniform across the nucleus surface, or that any jets present were too faint or too narrow to resolve at the angular resolution available from Earth orbit. The earlier Mars spacecraft observations had hinted at possible structure, possible jets, but from Spherex's more distant vantage point, such features, if they existed, blended into the overall glow. The telescope's measurements also addressed a fundamental question about 3I Atlas. How large is the actual nucleus, the solid core from which all this gas and dust is emanating? Previous estimates had been challenging, because you're trying to distinguish between light reflected from the solid nucleus and light reflected or emitted from the surrounding coma. At the distance of observation, the nucleus and inner coma blend together, making precise measurements difficult. The Spherex team approached this by assuming that all the continuum light they measured, the smooth background of reflected sunlight not associated with specific emission or absorption features, came from dust in the coma, and they compared this to estimates of how much light the nucleus itself would reflect, based on its assumed size and surface properties. If you assume the nucleus had an albedo, a reflectivity, of about 4%, typical for cometary nuclei which tend to be quite dark, covered in organic materials and radiation-processed ices, then the measurements suggested a radius of approximately 23 kilometers. This is large for a comet, though not extraordinarily so. For comparison, Hale-Bopp, one of the great comets visible from Earth in the 1990s, had a nucleus estimated at around 30 to 40 kilometers across. But 23 kilometers is substantially larger than many short-period comets that orbit the Sun regularly. It's large enough that the object contains significant mass, perhaps trillions of tons, enough that its internal structure might be complex, might have layers, might contain materials from different stages of its formation or from different regions of its parent protoplanetary disk. However, the size estimate came with considerable uncertainty. If the albedo was higher than 4%, if the surface was more reflective than assumed, then the actual nucleus would be smaller, perhaps much smaller. Some earlier estimates, based on different assumptions and different observations, had suggested a radius as small as about 3 kilometers. The truth likely lies somewhere in this range, but without direct imaging that resolves the nucleus clearly, without a spacecraft passing close enough to see the actual solid body separate from the surrounding coma, the exact size remains uncertain. What the Spherex observations confirmed, when combined with all the other measurements from ground-based telescopes, from the James Webb Space Telescope, from the spacecraft encounters, was that more than 99% of the light being detected from 3I Atlas came from the coma, from dust and gas surrounding the nucleus, rather than from the nucleus itself. This is typical for active comets. The solid body is small and dark. The coma, even though it's extraordinarily tenuous by everyday standards, contains enough material spread over such a large volume that it outshines the nucleus tremendously when you observe in visible and infrared wavelengths. As we've journeyed through these observations, through the chemistry and the emissions and the spacecraft encounters, and now these final infrared measurements, a picture has emerged of 3I Atlas that is both clearer and more mysterious than what we knew in early July, when it was first detected. We know it's large, or at least not tiny. We know it's active far from the Sun, releasing carbon dioxide as its primary volatile, with water playing a secondary role. We know it shows metal emissions that suggest unusual chemistry, or unusual release mechanisms. We know it likely originated from the thick disk of the galaxy, potentially 9 billion years ago, carrying within it the frozen memory of cosmic noon. But we don't know why its chemistry is so different from solar system comets. We don't know if the carbon dioxide dominance reflects its formation conditions, or billions of years of radiation processing, or some combination of factors we haven't fully considered. We don't know what's causing the efficient release of nickel atoms, while iron remains comparatively quiet. We don't know the exact size of the nucleus, its rotation state beyond that 8-hour, 22-minute period, its internal structure, whether it's a single solid body or a rubble pile held together by weak gravity. And soon, we won't be able to learn more, at least not from this particular visitor. 3I Atlas will pass through perihelion, will begin its outbound journey, will fade as it recedes from the Sun and becomes less active, less bright, eventually falling below the detection threshold of even our best telescopes. It will return to being what it was before July, a dark, frozen wanderer, invisible among the countless other objects drifting through the galaxy, knowable only when it happens to pass close enough to a star to warm and glow, and be detected by anyone who might be watching. Perhaps, if our civilization persists and advances, if we develop faster spacecraft and better propulsion systems, future interstellar visitors might be met not just with telescopes, but with probes, with missions launched quickly enough to intercept while the visitor is still in the inner solar system. Perhaps future astronomers will be able to study such objects up close, to land on their surfaces, to drill into their interiors, to bring samples back to Earth for detailed analysis. Perhaps the questions we're left with about 3i Atlas will be answered by observations of future visitors. Or perhaps not. Perhaps some mysteries are meant to remain partial, to be understood only incompletely, to remind us that the universe is vast, and our view is limited, and there will always be more to discover than we have time or resources to investigate fully. There's something peaceful in that acknowledgement, something that allows rest rather than demanding continued striving. The observations will continue for as long as the comet remains bright enough to study. Astronomers will track it through perihelion, measure how its activity changes as it rounds the sun, watch to see if anything unexpected happens at closest approach. They'll continue analysing the data already collected, looking for details they might have missed in the initial examination, comparing measurements from different instruments, building models that try to explain the full range of observations, and then, gradually, the attention will shift elsewhere. Other comets will become interesting. Other interstellar objects might be discovered. The rate at which we detect such visitors has been increasing as our survey capabilities improve, and there's reason to think that several such objects pass through the inner solar system each year. Most of them simply not bright enough or large enough to be noticed against the vastness of space. Future detections will add to the statistical sample, will help us understand whether 3i Atlas is typical or unusual, whether its chemistry represents a common pattern or a rare variation. The story we've traced tonight, this journey through discovery and chemistry and deep time and spacecraft encounters, is just one chapter in the larger story of how humanity learns about the universe. We detect something unexpected. We point our instruments at it. We measure what we can measure. We think carefully about what those measurements might mean. We propose explanations, test them against the data, refine our models. We share the findings with other scientists, who examine them critically, who suggest alternative interpretations, who design new observations to test competing ideas. It's a slow process, this building of understanding. It doesn't offer the instant gratification of immediate complete answers, but it's reliable, it's self-correcting. It accumulates over time into a body of knowledge that, while never perfect, becomes increasingly accurate, increasingly comprehensive, increasingly able to make predictions about what we'll find when we look at new objects or explore new regions of space. We have wandered through the story of 3i Atlas for a while now, following its glow from that first detection in July, through the accumulating observations of August and September, through the spacecraft encounters and the infrared measurements, through the questions about chemistry and origin and what it all might mean. The comet itself continues its journey, indifferent to our curiosity, following the mathematics of orbital mechanics, releasing molecules and atoms as the sun's warmth permits, slowly rotating, slowly approaching, and then slowly receding from the star around which we orbit. The question remains, as it always does with such visitors, what exactly is this thing? Where exactly did it come from? What can it tell us about the galaxy beyond our immediate stellar neighbourhood? We have partial answers, tentative conclusions, models that fit the data reasonably well, but we don't have certainty. Perhaps that's fitting. Perhaps the questions themselves are what matter. The reminder that the universe contains complexity we haven't fully mapped, chemistry we haven't completely catalogued, histories we're only beginning to read. For now, as sleep finally becomes irresistible, as the day's concerns fade and the mind drifts toward rest, let this thought settle with you. Somewhere in the space between Mars and the Sun, an ancient fragment of some long-ago planetary system continues to glow, continues to release its unusual chemistry into the vacuum, continues its temporary passage through our small corner of the cosmos. Tomorrow it will be slightly different, slightly changed by another day's worth of solar radiation, another day's worth of sublimation. But tonight, there is only the gentle awareness that such things exist, that the galaxy is full of travellers bearing witness to distant places and ancient times. We don't have final answers. We might never have completely final answers about this particular visitor, and somehow, that's all right. The mystery persists not because we're incapable of solving it, but because the universe is vast and old and complex, and even our best instruments and most careful reasoning can only illuminate small pieces of the whole at any given time. Thank you for wandering with me through this cosmic mystery, for letting your thoughts drift across millions of kilometers and billions of years, for holding space for wonder without demanding immediate resolution. Wherever you are, whatever brought you to this particular moment of quiet observation and gentle curiosity, I hope you found some measure of peace in the contemplation of ancient travellers and glowing metal atoms and the slow, patient work of understanding. The universe will still be here tomorrow, still full of questions, still offering opportunities for observation and thought. The comet will continue its journey whether we're watching or not. The atoms will continue streaming into space. The chemistry will continue unfolding according to principles that operated long before we existed and will continue long after we're gone. For now, let yourself drift into sleep, carried along by the rhythm of your own breathing, by the weight of the day releasing its hold, by the gentle knowledge that the cosmos is vast and patient and full of wonders we're only beginning to glimpse. The mysteries can wait. The questions will still be there in the morning. Tonight, there is only the soft darkness, the quiet hum of the universe continuing its work, and the peaceful descent into whatever dreams may come. Rest well, knowing that we live in an era when such observations are possible, when ancient visitors from other stars can be detected and measured and pondered, when human curiosity reaches across the gulf between worlds to touch, however briefly, something that has travelled farther and longer than our species has existed. It's a remarkable time to be alive, to be curious, to be wondering about what else might be out there, drifting through the galactic dark, waiting for someone to notice, to measure, to care. Sleep now, gently and deeply, with the awareness that the universe is working at scales, both vast and intimate, that chemistry unfolds atom by atom while galaxies turn slowly through the cosmic night, that somewhere between the immediate concerns of human life and the incomprehensible spans of deep time, there exists this moment, this breath, this gradual release into rest. The glow continues in the darkness between worlds. The measurements accumulate. The story remains unfinished, which is perhaps exactly as it should be. And you, having followed this particular thread of cosmic curiosity as far as it can carry you tonight, can let it go now, can release the need to know everything immediately, can trust that the universe will continue revealing itself slowly, patiently, in its own time. Good night, traveller. May your dreams be as vast and peaceful as the spaces between stars, where ancient comets drift and chemistry unfolds, and the universe continues its patient work of simply being, whether anyone is watching or not.